Okay, here are your notes on section 16.3. So now we're looking at the base strength or the base ionization constant, which we refer to as Kb. Okay, so strong bases, any kind of ionic hydroxides, okay, completely dissociate. And so it's really easy to find the concentration of our OH. We just use our dissociation equation, times it by our mole ratio, and we can find our concentration of OH. So those are for strong bases. We've looked at those before. Now we're gonna more focus on our weak bases to solve for these. Okay, so other entities that act as bases are collectively called weak bases because empirical evidence indicates that they attract protons less than hydroxide ions do. So the equilibrium of weak bases uses concepts similar to acids. Really, it's the same as acids, except now we're looking at bases, and it's going to produce hydroxide over here instead of hydronium. Okay, and so the equilibrium, we have our weak base. We just will refer to, like, for any weak base, it's just referred to as B, plus water is going to produce our conjugate acid and then hydroxide. So equilibrium constant for this general formula for Kb is going to be our product, so our conjugate acid times hydroxide divided by our concentration at equilibrium of our weak base. Okay, so Kb is just called our base ionization constant. Okay, note that the expression for Kb does not include pure water, because the same reason that our Ka doesn't. For acids, water is a liquid. It doesn't have a concentration. It's just pure water. So the conjugate base of a weak acid can also act as a weak base. So like the fluoride ion in this example is the conjugate base of hydrogen fluoride. It can act as a weak base when mixed with water to produce our hydrofluoric acid, okay, and hydroxide. And the Kb formula would look like this. Just move up here. Okay, so the reaction equilibrium equation for aqueous sodium citrate, again with sodium citrate, the citrate molecule is our weak base. The sodium is just a spectator ion, so we don't even write it. We just write our citrate times water produces our hydrogen citrate, which is our conjugate acid, and then hydroxide. Again, in our expression, our conjugate acid times our hydroxide divided by our divided by our weak base. Okay, just as the case with all our Ka values, there are two kinds of weak base solution calculations that involve the Kb constant. So we can calculate the Kb constant from empirical measured amount concentration data, okay, at equilibrium, or we can use a Kb value to predict the amount concentration of hydroxide ions for a known solution where the initial weak base concentration is known. So we can, like this first one, this can be like from ice tables and so on. Okay, this one was kind of working backwards. We're given the Kb, we might have to like the x squared over initial concentration and solving for them. Okay, here's an example problem. Okay, so one of the uses for aniline, okay, C6H5NH2, is the manufacturing of dyes. Aniline is soluble in water and acts as a weak base. When the solution contains 5 grams per liter of aniline that was prepared, the pH was found to be 8.68. Calculate the base ionization constant for aniline. Okay, and so again, what's required, we're looking for the Kb. We are given the formula for aniline. We're given the solution contains 5 grams per liter, and we're also given our pH. Okay, so always kind of plan out our strategy. So start with that. So step 1, you're going to calculate the molar concentration of the solution. Calculate the molar concentration of the solution using molar mass of aniline and mass of aniline dissolved in 1 liter of solution. Okay, then we're going to solve for our concentration of hydroxide. We're given the pH, we need to find the pOH, and then from the pOH we can find the concentration of hydroxide at equilibrium. And then we want to write the equilibrium equation and then set up our ice table. So here's kind of what we would do in step 4. Then we'd use those equilibrium terms to find our Kb. Okay, so, and there will be times, I guess you guys don't have to worry about this, there's no diploma this year, but okay, where they'll give you like grams per liter or something. You can always just use unit analysis to cancel out and get it to something that you know. So like we never use grams per liter for giving like concentrations. We need to find it in moles per liter. So we can find our concentration by dividing by our molar mass, gets rid of our grams, and then we get moles or liters, because when you divide by a fraction, you multiply by the reciprocal. That's why it's a lot easier to show this if you use unit analysis rather than actually dividing it out. Okay, then we need to calculate our pOH. So we are given our pH, so we need to go 14 minus our pH gives us our pOH, and then 10 to the negative pOH gives us our concentration of hydroxide. Okay, now we can set up our ice table. Okay, it's not showing it here, but like we would put this number in as our concentration at equilibrium for both our hydroxide and our weak base. And then if we know that this is our initial, and then we go minus this, but again, like if you look here, the significant digits won't matter, so this is going to actually stay the same. Then we can write our numbers into this Kb expression and solve for our Kb 4.3 times 10 to the minus 10. Okay, this example, again, like I won't do any examples out of your textbook because you can just look in your textbook and see it. This is on page 745 of your textbook. Okay, so look it over if you're struggling with any of these. Okay, and it shows you kind of the process of how to do it. I will do all of these examples on a separate video because I need to write them out, so I can't do them on here. Okay, so calculating the concentration of OH from our Kb. So this is similar to what we've done before when we were looking for like our hydronium value when we're given the Ka. Okay, so we need to use a relationship between the conjugate acid-base pairs. Okay, and if there's because there's no Kb values in our data booklet. So that's an important one. A lot of time we aren't going to be given the Kb. What we're given is the Ka in our data booklet, and then we're going to use these formulas to go from our Ka to find our Kb. So really this formula here is our main one. So the general formula, Kw, so again, that's an ionization of water, which is in your data booklet, it's 1.0 times 10 to the negative 14, okay, is equal to our Ka times our Kb. Because really we're looking at, like this is similar to our pH plus pOH equals 14, except we're basically going to use logs for we use logs for that one. We won't use logs for this one. Okay, and so our Kb, this is the main one we're using, so we're usually given a Ka in our data booklet. Okay, so we can find our Kb is just our Kw divided by our Ka. Okay, and so example here, okay, calculate the Kb for the conjugate base of benzoic acid. So you just look up the conjugate, or like the Ka for benzoic acid. Okay, and like you look up the Ka for benzoic acid, even though you're looking for the Kb for its conjugate base. So it goes from one to the other. Okay, so now we just find that because like sometimes you'll find these on both sides. You always want to use the Ka of the conjugate acid to whatever base you're looking for. Okay, so find that in your data booklet, 6.3 times 10 to the minus 5, go Kw divided by that, and you can find your Kb. Okay, for this one here, like you're given the Kb, you want to find the Ka. Okay, and so you just put it into the formula. Okay, these examples are also in your textbook here. Okay, so problem 16.4 is on page 747. Example 6 is on page 748. And again, like if you want to see any of these, just let me know and I can do video examples. Yeah, I will do video examples of like this one that isn't already in your textbook. So kind of a summary, what we're doing here. Okay, so a few general steps to guide us when we need to solve for an acid or base equilibrium problem. So first, recall in calculations involving the equilibrium constant, if the concentration of the reactants were at least 1,000 times greater than our equilibrium constant, you can make the approximation that the concentration of the reactants are the same as their initial concentrations. So it's called the rule of 1,000, and that makes things a lot easier. Okay, to kind of know when to use this, so if you write the chemical equation, use the chemical equation to set up an ICE table for reacting substances whenever initial acid or base concentrations are known. Enter the values into the table. For a problem that give you the initial concentration of the acid, compared the initial concentration of the acid with the acid ionization constant. Okay, again, if our initial concentration is greater than 1,000 times our Ka, okay, or like I always do it kind of the other way, initial concentration divided by Ka is greater than 1,000, okay, then our initial is going to be the same at equilibrium, so we can just carry that number down. If it doesn't work, we can't use this approximation method, so there's going to be a different way we can solve for it. Okay, and really for bases, it's the same thing. Okay, we can find if we know the Kb, and we go the initial concentration of the base divided by a Kb, if that's larger than 1,000, then our initial concentration will be the same at equilibrium. Okay, the effects of amphiprotic entities. So remember, an amphiprotic substance can work as both an acid or a base. So if you look on your formula sheet, there's a couple different things that you can find on both the left-hand side, like under acid formula, and the conjugate base formula. Okay, so depending on which one you want, okay, you really have to be careful there and know like if you want the conjugate base or the conjugate acid of that substance. Okay, so get the Ka value. You can always get the Ka values for all of these off of in our data booklets. Okay, and then we can find our Kb using our Kw. The higher the K value tells you which reaction is predominant. So basically, for this example here, it's in your textbook on page 750, but I'll kind of just read through it so we can know how to do it. So which reaction predominates when sodium hydrogen sulfite is dissolved in water to produce hydrogen sulfite solution? Okay, which will the solution be acidic or basic? So if we look in our formula sheet, our Ka4HSO3 is for the conjugate acid, so when it's acting as a base, is 6.3 times 10 to the minus 8. The conjugate acid, 1.4 times 10 to the minus 2. So for HSO3 negative, we can put those numbers in. Okay, 7.1 times 10 to the minus 13. So the Ka for hydrogen sulfide ion, okay, far exceeds the Kb value. So according to the Kw relationship and the equilibrium law, an aqueous solution of this substance will be acidic because the hydrogen sulfide ion will react predominantly as a Bronsted-Lowry acid. Okay, another way to kind of tell which one is just which one's higher, okay, is I guess that doesn't really work. It's not as simple as like that. So yeah, if you calculate these, and again, like if you want to see more examples, read through this, like page 750 in your textbook, or I can show you more examples later on. Well, and I'll do these examples on the next video. Okay, so we'll stop there. Okay, watch the video with examples. They hopefully will help you as you're working through. And again, I'll do a couple examples straight off your worksheet.